Well, welcome to the wonderful world of ultrasound. How many of you have attended either factory OEM training or third-party training? Just to show of hands on anything ultrasound. Okay, so we have a few. So the reason that my colleague and I came up with this program was because this subject matter is no longer presented in those forums. It's usually left up to you to self-learn some of this material, or get out the operator's manual, or which we all do all the time and read that. So we designed this from a service standpoint. What do service engineers, what do they find valuable in this? So the idea is to understand what the sonographer is saying, the lingo that they use. It'll help you differentiate between maybe a true malfunction or a user-induced type of problem. Understand how the systems are used clinically, as well as help make you guys change you or elevate you from a good service engineer to a great service engineer, just through some of these skills and some of this content. So, is there a way to dim the lights? Just because some of these images are more challenging to see. Sonographers do it in the dark, by the way. If you didn't know that. I'll leave ones up front too. Because some of these, we're looking at subtle changes in some of these images, and that's what I want to point out, and it's hard to see some of that with a lot of daylight. So one good rule of thumb, there we go, is that adjust the room lighting to a typical scanning room intensity, which is what we just did. So never try to judge image quality with the lights on, because it's not how the sonographers use the system. They use it in a dimly lit, almost no light condition, where they have a little reading lamp over in the corner. If you are going to make any changes to the monitor or the displays, always check with the sonographer or the customer that they approve with your changes. And the idea is you want to adjust this grayscale bar over here on the side so that you can see the darkest dark and the lightest white, but not have, if I look down here, there are more whites than there are darks. So, and the image is very white versus a lot of different shades of gray. So that's really why this grayscale bar is there on the system, is to make sure you have a good range of spectrum of color or grays there. And this is required for ACR accreditation, American College of Radiology. So it's something that either you or the radiation physicist or someone in the facility has to verify that the displays are adjusted correctly. So, pop quiz, does adjusting the system's main display, brightness, contrast, whatever, does that change the presentation of the image on a PAC system? Yes, no, maybe, no, it does not. Thank you for that. So everything that you do on the monitor is just affecting that. Everything else is sort of done through the software and back end of the scanner. So a little bit on probes. Nomenclature, how they are named, what those numbers and model numbers mean. In general, there are 3 or 4 styles of transducers. The top 3 being here, linear, gives a rectangular image. All the sound waves come out perpendicular to the probe. It's primarily used for vascular, intraoperative, and small parts. This is the most widely used probe in the space in ultrasound, mainly for OB/GYN, pregnancies, ovarian scans, abdominal. But the nice thing about these probes is the probe is relatively small, but you get a big image because the sound beams diverge from the probe, like that. And then these sector and vector probes are primarily used for cardiology use. For cardiology systems, we're looking at the heart, you have to find a window within the ribs to shine the sound waves into the chest cavity, because the bone within the rib cage just blocks all that sound. So it's a really small probe, but you end up with a really large image. And it does that through some fancy beam forming in the probe as well as in the scanner. And there are other types of probes out there, endocavity probes, transesophageal probes, but these are mainly the ones that you would come in contact day to day in radiology. So why are they called what they are called? There is no real standard as to why probes are named what they are, but there's some generalities. So an IC 5-9D intercavity, the IC 5 to 9 megahertz of frequency, and the D is just GE's D style connector versus GE's RS connector down here. So the IC 5-9D and the RIC 5-9 are similar, with the exception of this does real-time 4D imaging. We'll talk about 4D imaging, but it's still an intercavity probe working from 5 to 9 megahertz, but it's a mechanical 3D probe. And an RS style connector is just like a laptop style connector, really small profile, plugs into the side. You can see the C's, they're curved probes. X's, they're the newer probes from Philips that do live 3D imaging, really expensive. Siemens adds an HD onto some of their probes for high definition imaging. And so that's why these things are named what they're named. So some things you're going to measure if you are doing some quality assurance studies or assessments. You're going to talk in the language of a physicist or a radiologist or even the sonographer. They're going to be talking about resolution, how crisp and how sharp the image is. Couple different types of resolution. One is spatial, then there's contrast and temporal. But within spatial, you're looking at the ability to resolve or see two or more distinct targets that are lined up either side by side or one on top of the other. So that's the difference between lateral and axial. We really don't measure elevational resolution, but if you haven't seen one before, this is a mock-up of a tissue mimicking phantom, which is just a hunk of ballistics gel to simulate body tissue with a bunch of targets in it at various depths and patterns. But anyway, elevational resolution will change if, and it refers to the thickness of the sound beam coming out of the probe. But if this is my phantom and this is my probe, and I move the probe this way, you can alter the image because you're taking different slices of the phantom. You're not shooting straight perpendicular up and down. You might be moving it from side to side, and you get a little bit of different type of. You can actually make the probe give you a bad image by just not having it aligned on the phantom correctly. Contrast resolution talks about the difference. Can I distinguish the differences in tissue density? So phantoms usually have a series of targets of different density, and how it presents on the scanner is various shades of gray. And so can I distinguish between two different shades of gray that are really close together? And then temporal resolution, there's nothing that you can really measure on a phantom or use. It's just the result of some settings made on the scanner. So can we distinguish changes over time? We'll talk about that in a minute. No one really talks about A-mode imaging anymore. A-mode imaging was the first type of imaging or first type of ultrasound data. And it doesn't look like anything other than blips on an oscilloscope, some peaks and valleys. But it's the simplest form of ultrasound, but it's used to create the images that we see on the systems these days, and I'll expand upon that. So it's from one single crystal, we call crystals, or array element. And then, so we send out a sound beam, and anything that is reflected comes back and shows up as these blips on the oscilloscope. So the amplitude is the strength of the returning echo that hits the probe. And then this along the x-axis is the distance away from the probe. So this, if I stick this on my body, and this was a probe, and we're using A-mode imaging, this left edge, the transducer's up here, the probe's up here. This might be the skin. This might be the beginning of an artery. There's some space between the artery, and this might be the distal wall of the artery. And everything in here would be blood flowing. But it doesn't tell me that. This stuff was used for research and developing modern ultrasound that we understand today. And that's why it's sort of important I mention it. B-mode imaging is the type of imaging that's most common. You turn on a scanner and this is what you see, B-mode imaging, or it's brightness mode. It's the default mode of imaging. And so what we're looking at is this uses multiple lines of A-mode imaging that are lined up, stacked like a loaf of bread next to each other to make this image right here. Instead of looking at amplitudes and blips on the screen, we convert these amplitudes into various shades of gray. So something with high amplitude would be white, something with low amplitude or weak signals would be black or darker shades of gray. So that's where the A mode comes into all of this. But that's how this works. There's another mode of imaging that's seldom used. It's mostly used in cardiology. It's called M mode. And what we're looking at in this is A mode imaging over time. So I pick with the trackball, moving it around on the system, I can pick and choose which elements or crystals in the array I want to look at. And then I scroll that data over time. And so what I can see is changes in the cardiac wall motion. It's not used anywhere outside of cardiology, but you will run into this from time to time. And then we have various modes of Doppler imaging, or Doppler modes. One of the most common is called continuous wave Doppler. And the continuous wave Doppler is the type of Doppler that is used in those little portable Doppler units, the size of a phone. They use up in the ICU, and they put it on the peripheral vascular, and they listen to the circulation up in the ICU or ER, wherever that is. That's continuous wave Doppler. It's similar to pulsed wave Doppler, but continuous wave Doppler is always sending and receiving. It's moving so fast, it's capturing so much data that the scanner cannot display a B mode image. So all you get is a capture of the image that freezes on the screen, and then anything that moves in the line of the Doppler cursor will show up and audibly listen to this and scroll across the screen in the spectral Doppler. Continuous wave Doppler, because it's sending and receiving continuously, it's best used for high velocities. Where do we have that? In the heart. If you go down to general radiology and you hit the CW button on the scanner for continuous wave, it won't turn on because continuous wave Doppler is only used in cardiology. So although it can do it, the software just disables it. What's used everywhere else in imaging is pulse wave Doppler. Pulse wave Doppler, same type of principle. We're sending out and receiving sound waves, but we're sending, we're waiting, we're listening, and then we display. And what this does is, because we're not sending and receiving constantly, we have a little, what's called a sample volume up on the screen here, a cursor that I can move anywhere in the image here, and it's going to pinpoint the direction, the location, as well as the velocity of that blood. So it's very accurate and pinpoints that, whereas continuous wave Doppler just gives you anything moving along that axis where that cursor is. Color Doppler is just an offshoot of pulse wave Doppler. Instead of audibly listening to the Doppler, now we turn on color flow and we can watch the blood flow through the artery and the vein. Typically, I mean, back when I started, there was only blue and red color schemes on the monitors or on the ultrasound systems now, and they corresponded to anything flowing away from the probe would be blue, anything that's flowing towards the probe generally would be red. So typically you would have a color map along the side of here, and depending on the velocity, you would assign it a shade of color there. Now you can have any color scheme you want. You don't need blue and red. You can go from purple to yellow. Sonographers can make their own color maps up. to whatever they want them to be. There's another type of Doppler called power Doppler or energy Doppler, and that's what's here. This really shows the fill-in of all of the structure within the artery or vein or whatever we're looking at. So we don't get velocity information, we don't get directional information, we just fill in the vein and artery so we can see quality of flow. And then they created this thing probably about 10 years ago, tissue imaging Doppler, where we're not looking at the blood flow, we're looking at moving tissue. So right here it's the cardiac wall. Here's the atrium, the ventricles over here, the septal wall, the valves. You turn this on, you don't see the blood flowing, but you see the tissue moving. So it's to qualify the tissue that's moving in the structure, and it's mostly used in cardiology. So those are our Doppler modes. So here's what I call an applications-based artifact. You might find this with newer sonographers. Definitely students will experience this type of problem. But if they have one of the settings incorrect, and those are typically called scale or baseline, this is our spectral Doppler that's going across here. But if your scale is set wrong, the system will actually overlap. The peak of this waveform is actually rolled around to the bottom here. And what has to happen is someone has to change either the baseline here or the maximum scale over here, and then compresses it down. You know, a lot of times now you can hit a button and it'll auto scale, but not all scanners have that feature. And so, especially if you have, like I said, a newer sonographer, a student, or someone just hits the wrong, what I call preset on the scanner, they can cause this themselves and not even realize that they've done something. So that's an app, it's called Doppler aliasing. And that can happen in color mode as well. Ideally, you want your arteries and veins to be solid filled with a color. Like an artery, you'd want all red, and maybe with a vein, it would be blue. But it could be any color. But up here, what we run into is someone has misadjusted the scale and baseline. So instead of being all red, the red has wrapped around to the blue over here. So in this image up at the top, we are set to 0.23 centimeters per second. What's that mean? That's measuring the speed of the blood through an artery. Down here, it's changed to 0.46. So I bumped up the speed. I'm sensing faster flow down here than I am up here. So just like this peak wrapped around over here, the same thing is happening with this color scale over there. It's just a different mode of Doppler, and it presents it differently. Then we come into this stuff called 3D, 4D, 3D, 4D, and now 5D imaging. What's all that mean? So I'll spell it out for you here. 3D ultrasound is pretty much just a picture or a screen capture of a three-dimensional ultrasound. It's what we have on the image right over here. It's just a capture. Now, if I say 4D ultrasound, we don't have an image. We have sort of like a movie file, so we can watch the baby floating around in the womb. This is also a 4D ultrasound image. Sometimes it's called live 3D. Different manufacturers use different terminology. But here, I'm actually looking down inside a heart chamber, and I'm looking at the valves opening and closing. With the move of a trackball, I can rotate this up and around in free space in 3 dimensions and look at that and actually measure the volume in the heart chambers. And 3D, 4D is just a generic catch-all term that talks about probes or the technology. With 3D imaging, I mentioned here, you could have solid-state probes where everything is purely electronic, or you can have the old-school mechanical probes. And I had one at the desk today. Thing has a motor in it, and the array or the crystals wobble back and forth. And then we have this stuff called 5D imaging. There's no difference between 3D, 4D, or 5D other than 5D ultrasound makes this look like that. So it makes the baby look pretty or realistic. It's strictly a marketing term, and it's used to target the obstetrics market. So what's the difference? So 2D lets us visualize the length, width, and structure of an artery, so to speak. 3D lets us look down inside the artery. 4D, I turn that on. Now I can calculate the volume of blood moving through that artery. And 5D, just like I said, makes it look pretty. That's it. So there's no technology differences between in the scanner that makes a fourth or fifth dimension. They're just all marketing terms. That is it. So then anytime you turn on a scanner, plug in a probe, and you want to use that probe, the sonographer or you have to push a button called a preset. It initializes the probe. And by that, I mean it selects about probably 40 to 50 different settings on the scanner for a particular body or study type. So they'll have a preset for a carotid artery because the blood flow in the carotid is different than the blood flow in an extremity or the abdomen. We're looking at different depths, different speeds, different shades of gray, but it all does that with a push of a button called a preset. So there are factory presets on every scanner that come pre-configured from the factory. You can't change those. But there's usually someone from the OEM in there, in the radiology department or cardiology department, when the customer purchases that scanner, and what they do with their applications engineers, they set up custom presets to Sally's sonographer or Joe the sound guy. You know, he wants his color maps this way. He wants these presets. So they're custom presets. These things can become corrupted. They can become overwritten. And so they don't work the way they think they work or have been working for the last few months. The key to this is, as a service engineer, every PM you want to back up your presets. And then you take a backup of your backup because at some point you might lose that first backup. These are things that can be restored pretty much in minutes. If you don't have a backup, then someone from the factory has to come in and work with the sonographers again to reestablish all of those presets. Now, if you have a GE Logic E9 down in this room that has a set of presets, you can copy the presets from the Logic E9 here down to there, but you can't do that from an E9 to an E10 or a Voluson to a Logic. It's different softwares for different platforms by the different manufacturers. So one of the main controls on an ultrasound system is called acoustic power. It's like the volume control on your radio. Turning that up puts more output out of your speakers. Sonographers are taught to use as little acoustic output as possible. There's really been no studies to say that ultrasound energy is harmful, but since we don't know that, even though it's been around, sonographers try to use as little sound energy as possible to get a good quality image. The thing is, most default presets on the scanner set the acoustic output to 100% because that gives you the biggest, brightest, highest quality picture. However, you can actually overheat a probe if you're doing too much with it at one time. So if your acoustic output is always set to 100 and you're imaging in B mode and in color and in Doppler and throw on 3D, you can actually cause the probe to overheat because you're firing it too many times to do that. That's okay. The scanner has software built into it to freeze or disable the probe if it gets too hot. It'll pop up an error message, over temperature issue or over temperature error. And a lot of sonographers think that there's something wrong with the probe, and there very well could be. However, it's usually an applications issue. They're doing too much at one time with the probe, and it is just getting warm. So it's a safety system. It may not indicate that there's true problem, other than the way they're using the probe, no hardware issues. Typically, acoustic output, it's rated one way or the other, either percent or decibels. Obviously, 100% is full power, and you can back that off. But sometimes it's done in dB, where 0 dB is 100%, and for every negative 3 dB, you're dropping that 50%. It's just different OEMs choose different ways to present that. The opposite of acoustic output is gain. So we have Grandpa sitting watching his baseball game, if that's what he likes, over in the corner, and he can't hear it. So what does he do? He turns up the volume on the TV. Well, everyone else in the room is getting blasted out. They can't talk to themselves because the TV is so loud. Well, Grandpa, turn down the acoustic output and turn up the gain on your hearing aid. Gain is like turning up the receivers on the scanner. So we listen more versus transmit more. It's always better to listen more than to talk. And that's always been my philosophy. Listen, that's why we have 2 ears and only 1 mouth. But that's what gain is. It amplifies the received echoes from the probe. And so these are the same images, the same probe. We've just turned up or down the gain. The top images has 17 dB. This has -4. And it all comes down to user preference. Sonographers will play around with the gain until they get it looking the way they want it to look at. They're not saying, I need 4 dB or I need 17. They're just playing around until they get it to look the way they want to see it.
Are there oftentimes like auto
gain?
Yeah,
Mm-hmm.
Yeah. For these types of settings, like the user isn't necessarily setting these every time they're taking image.
Right. It's one of the things that in a preset you can select whether you want auto gain on or off. Typically, as soon you start scanning, the auto gain kicks in and auto adjusts. But if you make a change to that, the setting, it sort of disables that temporarily. But yeah, that's a good point. The newer scanners have this auto gain, and different manufacturers call it different names. Another way of boosting the receiver's amplification or gain is through either DGC, TGC, or LGCs. Depending on who made the scanner, you will call these horizontal sliders time gain compensation or depth gain compensation. Siemens uses Ds, everyone else uses Ts. This is lateral gain control or compensation. So what this does, these boost the gain based on the depth of the image. So up here, if I move this side to side, left makes the image darker, sliding it over to the right makes the top of the image very bright. Likewise, down here, it'd be the bottom of the image will be either lighter or darker. And sonographers are always playing around with these things, running their fingers up and down to get the right background information. And these things, these LGCs, if you have one the whole way up or down, you can make a horizontal line in your image, either white or a dark line in the image. So you can actually make a probe or a system look bad if these aren't adjusted correctly. And typically, they're just equal with each other. Sometimes they're in a little V. Cardiology systems like to have these in a little V or a U shape. But it's a user preference thing. The other thing is transducer frequencies. Sonographers have the ability to change or utilize different frequencies in the probe. Low frequencies offer great penetration, a little fuzzier image. High frequencies give you great resolution, but you can't penetrate and go really deep. So there's always going to be a trade-off with ultrasound, and it comes down to just the physics of how ultrasound works. You can either penetrate or you can have high resolution. You can get a little balance there because modern probes have these use a spectrum of frequencies that are selectable. If you use a Philips system, you're not actually selecting the frequency of a probe, but you're selecting, you want more resolution, you want more penetration, or just general. Where GE or Siemens, you can actually look at the frequency up on the scanner and bump it up or bump it down and look at the frequency changes that you're changing to. And so this is the same probe, the same anatomy. We're just using a different frequency. So up at the top, I'm using 2 megahertz. Here I'm using 4 megahertz. And all I want to point out is this image is what I would say is a little smoother. This is more grainier, more black and white. You're not really going to see a difference in penetration between 2 and 4 megahertz. Now, if I bump that up to 6 or 8, you're not going to see anything maybe past this point. It all just drop off from attenuation. But what you do with higher frequencies, you just gain a little bit more definition in the details. The idea is always use the highest frequency possible because that gives you the highest resolution. Well, it's tough with mom who comes in pregnant and her belly is out to here, 6, 7 months pregnant. You have to penetrate through, how many centimeters of tissue to get a high-res image. Sometimes in OB, they will use an endocavity probe, and they'll insert that into the birth canal, and then go right up next to the cervix, and you get a high-resolution picture of baby there. Because you're closer, you can use high resolution. Harmonic imaging has been around for 15, 20 years. What harmonic imaging does is we transmit at one frequency and we listen at a higher frequency. It could be 2 times or 4 times the frequency that we're transmitting out. We're listening at, say, 2 times the frequency. Why would we want to do that? Well, someone found out at some point that we can eliminate some of the fill-in inside of hollow structures like a cyst. So we can get rid of some of this, what I call speckle or background, and you can actually see more of the fluid that's inside of there by turning on harmonics. Some of the things that I'm going to get talking about now are all software generated corrections. And you can through some of these corrections, you can actually make a good probe or a healthy system provide a good image. Likewise, you can have a bad or faulty probe or system, and you can compensate for it using some of these controls. You can mask some problems with the front end of the scanner or the probe by using some of these corrections. When we teach QC image testing, we always tell people, disable all of the corrections. Turn off harmonics, turn off what I'm going to get to in a minute, some speckle reduction and some other things, because they mask over the image and hide a lot of things. Dynamic range is another setting. It's set up during the preset, and all it's doing is saying, this is the range of the shades of gray I want to use to describe this image. Do I want to be more descriptive and use more shades of gray, or do I want to use 5 shades of gray, which isn't realistic? But in essence, that's what we're doing with dynamic range. And let's see. Here's a better example of some pictures. So this top image is very black and white, very gray, I would say a little grainy. This one has smooth images. There are more shades of gray to describe this image than there. Very white and black images, more shades of gray. And that comes down to a user preference. Cardiologists like very black and white images. Radiology, OB, they like things described in more different shades of gray. They like smoother images. Cardiologists, for some reason, like very black and white images. Don't know. That's just how it's been. The probes themselves that they handle and use, they have an acoustic lens on them. It's the rubber membrane on the probe that contacts the patient. There's a thickness to that. There's a precision curvature to that, and that provides mechanical focus to the energy coming out of the probe. However, the scanner itself can focus the sound beams electronically at varying depths. So there's a little paddle or a button or a knob you can turn, and you can move a caret or some kind of indicator up and down in the image, and that tells you where all the energy and where the image is going to be focused, mostly. You can have up to, from 1 to up to 8 different focal zones in an image. And every time we add a focal point in an image, we're actually firing the probe one time more. So for every, to make an image, we fire this probe, we listen. To make an image that has two focal zones, I fire it once for the focal zone for once, fire it again for the second focal point, and then I paint the image. If I have 8 focal zones, I'm firing this probe 8 times to make one frame of ultrasound information, because that's the focus at each depth, and then it paints the image. That's just the way the software works. So what does that do? That turns down or automatically changes what we call the temporal resolution, how fast the screen is updated. And I'll talk about that in a minute. But where there's a trade-off is you lose temporal resolution, but you gain spatial resolution. You get a sharper picture, but the screen doesn't update as fast. And one thing that you will notice on GE scanners, they're the only OEM that has this happen, is what we call a stitching artifact. There's a horizontal line here. You can see it way in the back. So there's one area here, there's another area here. That's the result of stitching the images together with all these, these 3 focal zones that I have over here. No other OEMs experience this. That's just the way their scanners and their software work. There's nothing wrong with the system or the probe. That's just a result of how they paint their image on the screen. A lot of folks will send probes into us because they think that's a problem, and it's not. So that's when I get on the phone and explain to them that it's an artifact of the system and the image itself. So frame rate. Every scanner has the ability, and somewhere on the screen will tell you the frame rate or the refresh rate. How fast is the screen updating? So this is set at 10 Hertz. It's being updated 10 times a second. If I have, and what I have here is 1, 2, 3, 4, 5 focal zones. So the screen, if I got rid of 4 of these focal zones, the frame rate would probably jump up to 33. Because we can now fire the probe faster, and we're not painting the screen 5 times to make one image. We're painting it once to make one image. And so this is important to cardiologists. They always want a high frame rate. Why? Well, because the heart's beating 60, 90 times a second. If we put all these focal zones in, we're going to miss 3 heartbeats before the scanner can paint the screen. But you will get a really crisp, sharp picture. But it doesn't do them any good because they're looking at that heart motion. And there's nothing you can do to change this other than getting rid of or adding focal zones, making an image not scan as deep or with less density, what I call line density, less resolution in here. So this frame rate is automatically calculated based on how the frequency of the probe, how far down you're scanning into the anatomy, how many focal zones. The speed of sound is constant. We cannot change it. So the sound coming out of this probe into my body is like 1340 meters per second. It's no faster, no slower. The scanner cannot process anything faster than the speed of sound that is waiting for it to go and echo back and hit the probe. And that's why this frame rate is sort of so important to cardiologists is because they need those fast updates. But that's what it's based on, that frame rate. There's another setting on a scanner. It's usually called space-time or resolution. We can change these settings to make an image or the probe or the system focus more on resolution or frame rate. So rather than change all those focal zones and do this and do that, I can take another, sort of like a master control, and I can tell the scanner through software to focus more on resolution or on speed or resolution, sharpness through this control. And then there's another control called either pre-processing or edge. And so what this does, again, it's through software. Do we want to focus more on the edges of different structures, or do we want everything to sort of be smooth? If we're in a vascular lab, we want to see the arteries and the veins in the peripheral vascular system. They want to see if there are any aneurysms or any bulges or any weak spots. So they want to focus on the walls of the arteries. So they might turn up the edge or the sharpness, whereas it's not as important, say, in cardiology. And there's another thing called frame averaging or persistence. I talked about painting the screen. For an image that has 5 focal zones, we're going to fire the probe 5 times and then paint the image on the screen. Then we're going to do it again, and we're going to do it again. And that's what this frame averaging and persistence is. How fast is the screen updating? How many frames are we averaging to make this image? Even if I have 1 focal zone, I can average 5 frames together through software to make the image look really smooth versus looking at every single image live. And so it's a matter of, if I move this probe fast across my body and don't average the frames together, I'm going to see that probe moving actively very fast. But if I'm still going like this and turn the frame averaging up, the screen's going to be a little jittery because it's averaging some of those frames together just to make one image. Again, this is all done through the applications folks that come on site and set up these presets, but sonographers can sometimes get lost in all these settings if they tweak the wrong thing or bump a button by mistake. There's another type of control called gray map or post-processing. And this has to do with, again, how many different shades of gray do I want to use to describe this image versus that image? It's sort of like dynamic range. Whereas, this image is more black and white, this is more smooth. It's just a different setting called post-processing or gray map. And there's another thing that sonographers might do. They might add a color overlay on top of an image, and it's just because in some conditions it's easier to see structures with some color versus black and white. So they make yellow masks and blue mask and magenta, whatever your favorite sonographer likes to use. But sometimes that helps them see the structures a little differently than just black and white. Here's another correction, a software correction out there that we disable anytime we're testing probes or the system. It's called Speckle reduction imaging. That's what SRI is. Philips calls it XRES. I forget who calls it UScan. But what we want to do is, and you can't see it with the light here, but subtly there is some speckling that's inside this hollow cyst or this vein or whatever this is. By turning on SRI, I can get rid of the speckling that fills in some of these hollow structures. And so I can focus on the anatomy or the vein or the organ that I'm looking at and not worry about maybe what's inside of it. Compound imaging, another software correction. Typically, if this is not turned on, all of the sound waves go down straight. If I'm using a linear probe, go perpendicular to the probe. If I turn on crossbeam, I fire the probe in multiple directions to make one image. And why would I want to do that? It's because with this turned on, I can sort of see around the corners of the structure in there. And so rather than have this, I end up with this. This has some little more definition to it. I don't know what this thing is, that structure, but I really can't visualize that up here. But turning on crossbeam lets me see around different structures by firing the probe in different orientations. So some image artifacts that you may come in contact with or your customer calls you with is what I want to talk about next. One of the primary points of failure, whether it's a system or a probe, if it's a system, I might be software, but with probe problems, It's a vertical black line or shadowy area in the image there. That's definitely something that is not wanted. That's typically called image dropout. It can be caused by any number of things. Any component that causes a single element in the array or crystal in the probe not to fire, not to send and receive, will cause that. It could be the probe itself. Someone could have dropped the probe and it hit the crystals or the array, and those crystals no longer function. You end up with that line. But it very well could be the probe cable. Over time, every single cable known to mankind is going to break down at the strain relief from overflexing. It's just the way life is in our world. So again, that can cause the crystal not to fire if there's an intermittent connection in the wire. Or someone could have just pulled some wires pulled the probe off the scanner, or ran over the cable with a caster on the scanner, and you end up with a dead spot in a cable. Likewise, you could end up with some bent pins inside the connector. There are over 100 pins inside of the connectors, and if someone's in a hurry and doesn't align that pin bank up just right, you can bend just one or multiple pins inside of the probe connector. Likewise, you can do the same thing to the connector on the scanner itself. Then you have a real problem if you have bent pins. If you have a probe with a bent pin, you take it down the hole and plug it into another scanner, you could corrupt the mechanics on that scanner. And then if they take that probe down to another scanner and plug it in, the bent pin on the probe could damage that other scanner. And you can chase problems around until someone looks at it and says, oh, I have a bent pin on my probe. The newer GE scanners out there and the Siemens scanners, their probes have what we call pinless connectors. It just looks like a faceplate on it. Inside the scanner are the male pins or the counterparts that will contact the various points of that plate. So inside the scanner, you could bend pins as if you plug in the probe haphazardly. Likewise, those pins inside the scanner are fractions of a millimeter in height. So that's one area on a PM where you want to clean out the ports on a scanner, because dust will impregnate those micro pins, and then you'll get some crosstalk between the different connections. So it's a good thing to do during a PM is to clean the scanner ports if you have those pinless type of connections. And it's likewise, it could be the front end scanner of the scanner that's bad, but work your way from the outside into the scanner. Don't just assume it's the scanner at first. So work your way from the outside in. The second, second very popular type of problem that you're going to run into is noise artifact in color Doppler mode. And let's see, what I'm showing is up here, see some blinking, or you get a wide band of color noise in the image. This stuff is not wanted. This is overlaying the circulation data over there. It's just like speckling of color that's just scattered throughout the image. This is typically two schools of thought. It could be a cable failure. You bend the probe and the cable, and every time the cable makes and breaks contact, you get a flash of color in your image. So that's indicative of a cable failure. However, if you're not seeing that, whenever you wiggle the cable, most likely you're running into electromagnetic interference. The probe is acting like an antenna. It's picking up RF energy from this thing, from the treadmill down the hall, from the landline phone that is ringing down the hall 2 doors down. Yes, that chased us around for 2 months. A landline phone causing an artifact like that. An elevator going up and down the elevator shaft right behind the scan room caused someone headache for 3 months. Every time the elevator went by, that got injected into the screen. I had an issue for several months. There was a microwave oven, a floor above the scan room. It only acted up during break times because that's when people went to it. So it wasn't all the time. So I chased this problem around until I eliminated possibilities did I actually find the problem. So these types of problems are pretty much addressed through process of elimination. I have a troubleshooting tree that you guys can use or reference. I have some articles on our website that talk about how to troubleshoot these types of things, or I can email them to you as well. But that's what I've got for you guys. Happy to share this with you.
What is the website?
Innovatusimaging.com. If you just go on our blog or website and search for color noise. But if you'd reach out to me, I can send you those in PDF forms as well. But we have all this stuff on our website as well, in our blogs. If you run into artifact problems, please use me as a resource. I'm happy to help you guys out any way I can.
Thank you.
Thank you.
Yep. Thank you guys.